This is you right now. This is you after you realize you have to learn about kinetics. That's okay though, we got you covered. Kinetics is the study of the speed with which reactants are converted to products. The speed at which the reaction occurs is more specifically known as the reaction rate. The reaction rate of a reaction is the rate at which the concentration of reactants decreases. And as time passes on, reaction rate also decreases because the forward reaction and the reverse reaction approach the same rate as the reaction goes to equilibrium. It is possible to find the instantaneous rate of the reaction by deriving the time versus concentration curve. Now let's talk about rate laws. These are formulas that can be used to determine the rate of reaction at any point in time using the current concentration of products or reactants, and they can only be found through experimentation. The formula shown is a general form of a rate law, and as you can see, the value of the exponent determines the order of the reaction. A reaction order of 0 indicates the reaction is dictated by a catalyst. The speed of the reaction is limited only by its surface area. A first-order reaction indicates that the slowest elementary reaction in the mechanism involves only 1 mole of the original reactants. A second-order reaction, like a first-order reaction, indicates the slowest elementary reaction in the mechanism involves only 2 moles of the original reactants. By integrating each of the rate laws, we can now find the current concentration at any given point of time using only the time, k, and the initial concentration. To determine the order in an integrated rate law, 3 graphs can be plotted. If the concentration versus time graph is linear, the order is 0. If the natural log versus time graph is linear, it's order 1. And if the 1 over concentration versus time graph is linear, the order is 2. Remember, the order of a reaction can only be determined by experiment, not by the mole ratios in a balanced equation. Now, let's look at a reaction with 2 reactants instead of just 1. In this example, we're given the concentrations of A, B, and the reaction rate. This information can be used to determine the exponents of A and B. Let's go see how now. If we plug in the values from trial 1 and 2 into the rate law equation, we can determine the value of B, and a similar process can be used to determine the value of A using trials 2 and 3. Now let's move on to reaction mechanisms. In order for most complex reactions to occur, multiple other steps must occur beforehand. These reactions, called elementary steps, cannot be broken down any further and add up to the original reaction. The stepwise reactions as a collective are called a reaction mechanism. The slowest of the elementary steps determines the speed of the overall reaction. Imagine a supply chain where one of the workers is working slowly. The product will gather around the slowest worker, and the rest of the factory can only output their product as fast as the slowest worker. The rate law of each elementary step can be written from its molecularity, or the number of species that must collide to produce the reaction. The coefficient of a species simply becomes the exponent in the rate law. Most reactions involve 1 or 2 species. Reactions involving 3 species are rare because they must all collide exactly at the same time, and the probability of this is low. A reaction mechanism must satisfy 2 requirements. The sum of the elementary steps must give the overall balanced equation of the reaction, and the mechanism must agree with the experimentally determined rate law. Now you might be wondering, this is all great, but how do we change the speed of a reaction other than changing the concentration of the reactants? Let's find out now. Reactions can be sped up by using catalysts, which lower the activation energy without being consumed by the reaction. The activation energy is the reaction's energy threshold that must be overcome to initiate the reaction. Lowering this energy makes the reaction easier to occur because of the less energy needed.
You ready? You ready? For those of you who want to know what kinetics is all about, it's like this, y'all. Order 0 is linear when it's A over time. Order 1 when L and A is a straight line. Order 2 is a line when it's 1 over A. To prove this, all you have to do is integrate. Order 0 is linear when it's A over time. Order 1 when L and A is a straight line. Order 2 is a line when it's 1 over A. To prove this, all you have to do is integrate. Speed, the reaction, is the rate. The forward rate lessens as time goes away. But the real reaction never terminates. I know this is a lot of knowledge to take in. The reaction is facing the catalyzation to make it. Lower energy activation. The reactant has space to race and lower its concentration. Each one can vary from slow to fast, but the slow one just slows down the task. Its reaction is made of elementary steps. The reaction determined rate is slower than the rest. The speeds of the best might sound like a mess, but please just trust the process. It's a lot to process. I suggest you find the rate law through an experiment. The rate is a concentration to the power of the order times a constant called K to account for disorder. If you are still in horror, maybe even on the border, in order to find the order, please just use trial and error. What if the order is 4 though? Don't get cornered, we are not answering that. You can go to nor though, we are only looking at 0, 1 and 2, but not 3 and not 4 though. But then they ask me, little b, what if we had more reactants? Hey, what about 3? You see, you just need to add another letter B to the order of B. That order is found experimentally. To make it clean, the formula's on the screen. Credit goes to Hank Green, but if you understand what this verse means, you can also join me and tackle this fiend.
Thanks for watching, and put this knowledge to good use by speeding up reactions all around you.